Imagine querying a corporate database for distributed workforce policies. If the stored documents only contain the phrase remote work or work from home, a standard keyword search will return 0 results. It searches for exact characters. This side-by-side comparison shows the limitation. The left terminal fails entirely, but the vector database on the right runs the exact same query and, in a fraction of a second, locates the remote work policy, even though the words distributed workforce never appear in the text. This gap defines the central bottleneck of retrieval augmented generation, or RAG. An AI model can only generate accurate answers if the underlying retrieval mechanism successfully finds the correct context. Traditional search systems rely purely on lexical matching. They map strings of text against other strings of text. This approach fails when human intent diverges from the specific vocabulary used in a document. Solving this requires a shift from word strings to multidimensional geometry. We are going to deconstruct the architecture of semantic search, tracing the mathematical limitations of keyword algorithms through to the computational execution of modern vector databases. Engineering reliable AI outputs demands a system built to retrieve underlying meaning. The architecture must prioritize conceptual intent over syntactic matching. The foundation of traditional search is term frequency. Algorithms scan a corpus of text and count how often specific keywords appear. This matrix visualizes a ranking algorithm known as BM25. The columns represent documents, and the rows track the frequency and uniqueness of exact tokens, like equipment, policy, or furniture. If present, it receives a numerical score. If missing, the space remains empty. When querying for allowance against a document discussing reimbursement, the algorithm assigns a hard 0. Because the exact string allowance is missing, the match fails. BM25 processes string frequency with high precision, but it lacks the logic to evaluate context. This forces the user to guess the precise vocabulary used by the document's author to yield a result. Relying on exact match keyword indices fails, because human language expresses identical concepts through highly variable syntax. To capture true semantic meaning, the architecture uses embedding models. These models use millions of learned parameters to evaluate how words relate. Instead of outputting text strings, these models map sentences into a dense 384-dimensional vector space. This coordinate graph illustrates how subjective meaning translates into exact geometric coordinates. A sentence like "dogs are allowed" is plotted at one point. A related term like "pets" lands physically close to that node. Meanwhile, a different concept like "remote work" is pushed into a distant quadrant. By plotting these points, the model creates vector clusters representing associated concepts. Dogs and pets are lexically distinct, yet their semantic similarity forces them into adjacent coordinate space. Conceptually unrelated ideas are pushed into distant coordinates, mathematically isolating them from the target search area. By translating language into high-dimensional space, embedding models convert the abstract concept of meaning into quantifiable data. Once the text is embedded, the system must calculate the exact distance between a query vector and a stored document vector across 384 dimensions. This calculation visualization shows the mathematical solution, the dot product. We can see a simplified version here using the arrays 1, 5, and 2, 4. The operation multiplies the corresponding values in each vector and sums those results together. This sum is passed through a normalization function to output a similarity score between 0 and 1. A high normalized score, such as 0.73, confirms a high semantic overlap between the query and the text. Unrelated concepts generate low scores. When we calculate the distance between remote work and pets, the output drops to 0.36. The database then ranks these results to determine which document chunks to return. The dot product replaces linguistic interpretation with mathematics to prove contextual relevance. A corporate system holds millions of document chunks. Running exact dot product calculations against every single chunk for every query creates a massive processing bottleneck. This diagram illustrates a brute force approach. It is an unscalable operation that runs in O of n linear time. As the document count grows, the computational cost rises aggressively. Vector databases bypass this bottleneck using structured indexing. The primary indexing algorithm for this task is Hierarchical Navigable Small World, or HNSW. It pre-organizes the vectors in memory, drawing connections between the most similar nodes to form multi-layered, clustered neighborhoods. When a search begins, the query drops into the sparse top layer of this graph. It hops through connections to quickly isolate the target neighborhood without scanning every node in the field. This is an approximate nearest neighbor search. By traversing the graph, retrieval time drops from linear scaling to logarithmic scaling. HNSW is the critical architectural bridge that allows vector databases to execute complex semantic searches in sub-second timeframes. This system flowchart tracks the complete pipeline. A user query enters the embedding model, converts into a vector, navigates the HNSW index, verifies relevance via the dot product, and extracts the most relevant document chunks. The heavy lifting, splitting documents into 500-character chunks, encoding them, and building the index, happens in a pre-processing phase before a user asks a question. The retrieval phase operates dynamically, mapping intent to vector space in real time. During the final augmentation phase, the system merges the retrieved chunks with the original user query and feeds that context into the large language model to generate the final response. Deploying this pipeline in production introduces strict latency requirements, as every step involves computationally expensive operations. To maintain performance, engineers implement multi-layered caching. Storing computed vectors and final answers for common queries allows the system to bypass expensive computations. Maintaining high throughput requires a precise, realistic balance of document chunk sizes, embedding models, and cache expiration times. Building robust RAG systems is an architectural challenge. It requires knotting human intent into scalable mathematical geometry.